In this program today, we'll discuss the silicon controlled rectifier, that is the SCR. This small device is capable of controlling huge amounts of power very precisely, and for this very reason it finds an extensive use in the industry. For controlling automatic operations very precisely, accurate control of power has to be achieved. This type of precise and accurate control is done by this very device, that is SCR. We'll first study the structure of the SCR. This device, as you can see, has got three terminals: anode, gate, and cathode. In order to study the internal structure of the SCR, we will take the help of graphics. It comprises of four layers: P1, N1, P2, and N2. Layers P1 and P2 are of P-type silicon, and layers N1 and N2 are of N-type silicon. These four layers form three junctions between them: J1, J2, and J3. These layers are connected with the three terminals: anode, gate, and cathode. In the absence of any external voltage, depletion layers are formed at junctions J1, J2, and J3. SCR is symbolically represented like this. That completes the description of the structure of the SCR. Now let us study its behavior by plotting the VI characteristics. In order to plot the VI characteristics, we need to apply a voltage across the device and then measure the current flowing through it. Now let us have a look at this circuit diagram. As you see, a voltage VAA has been applied to make the anode positive with respect to the cathode. A voltmeter has been put to measure the voltage across the SCR, and a milliammeter to measure the current flowing through it. In addition, we have put this resistance R to limit the value of anode current. Let us now actually perform the experiment to plot the VI characteristics of the SCR. This is the board that we would be using to measure the characteristics of the SCR. This is the SCR of which we would be measuring the characteristics. This is the voltmeter that would measure the voltage across the SCR. This is the ammeter that would measure the current flowing through the SCR. This resistance has been put to limit the current flowing through the SCR. This voltmeter would measure the voltage applied across the circuit, which can be varied using this knob. Now let us vary the voltage. You see that some current is flowing through the SCR. The current is approximately 80 microamperes. The voltage across the SCR roughly equals the applied voltage. Now let us see what is happening inside the SCR. When anode is positive with respect to the cathode, junctions J1 and J3 are forward biased and junction J2 is reverse biased. Therefore, depletion layer at J2 is wider. In fact, the whole of applied voltage appears across J2. Thus, no current can flow through the device. However, while doing the experiment, we had seen a deflection of about 80 microamps. But why did the current flow? Actually, through a reverse bias junction, only reverse saturation current flows. It was this reverse saturation current that was flowing through the device. It was of course very small, a few microamperes only. So far, the current flowing through the SCR was of the order of a few microamperes only. Therefore, we had used a microammeter to measure the current flowing through it. But as we would see later, several milliamperes of current can flow through the SCR. Therefore, we have replaced the microammeter with a milliammeter. Let us now further increase the voltage and see what happens. I further increase the supply voltage. Current being just a few microamps, you can't see a deflection. Oh, what has happened? The current through the device is increased and the voltage across it has fallen. Let us watch that again. I increase the voltage. Now it is about 100 volts. I increase it further. At about 115 volts, the current through the SCR increases abruptly and the voltage across it falls. But why does that happen? Before we try and find an answer to that question, let us see what happens if we further increase the supply voltage. As I increase the supply, the current also increases. Therefore, we see that at a certain voltage, the current through the SCR increases abruptly and the voltage across it falls. If we increase the supply voltage further, then the current continues to increase, whereas the voltage remains constant. Therefore, we can say that the SCR has behaved like a switch. At a certain voltage, it turns on, and subsequent increase in supply voltage leads to increase in current, but the voltage across SCR remains constant. But why does SCR behave like that? Let us try to understand that. As the anode is positive with respect to the cathode, junctions J1 and J3 are forward biased. Therefore, electrons and holes can cross junctions J1 and J3 easily. Say, two holes move from P1 to N1 and cross the junction J1. One may recombine with an electron in N1 region. Hole being a minority carrier in N1 crosses over J2 and reaches P2 region. On reaching P2, it temporarily increases the bias on J3. This causes two electrons to cross over from N2 to P2. Again, one may recombine and the other being a minority carrier crosses over to N1. On reaching N1, it temporarily increases further the bias on J1, thus causing three holes to cross over from P1 to N1. Again, Two of them cross over to P2 and increase bias on J3. This leads to even more electrons, 3 now, to cross over from N2 to P2. Of these, 2 cross over to N1, further increasing the bias on J1. And this process continues. This builds up a positive feedback, and a stage comes when concentration of holes in P2 and that of electrons in N1 becomes so high that the donor and acceptor atoms in the depletion layer at J2 are fully compensated. Thus, the depletion layer at J2 disappears. That is why the current through SCR increases and the voltage across it falls. The SCR turns on and there is a free flow of electrons and holes. Only body resistance and drop across J1 and J3 limits the current now. Drop across SCR is very small, of the order of 1 volt, and it remains almost constant. Hence, further increase in applied voltage leads to linear increase in current. Thus we see that the SCR behaves like a switch. When a voltage called breakover voltage is applied, it turns on. The value of anode voltage at which the SCR turns on when the gate current is equal to 0 is known as breakover voltage VBO. Thus, the VI characteristics of the SCR so far have a form like this. As long as the anode voltage is less than the breakover voltage, the current is very small. When anode voltage becomes equal to breakover voltage, the anode current increases and the anode voltage falls. Subsequent increase in supply voltage causes the anode current to increase, whereas the voltage across the device remains almost constant. I hope that with these explanations, the turning on behavior of the SCR must be clear by now. Now let us reduce the voltage and see what happens. We had earlier seen that the SCR turns on at 115 volts, and therefore we expect it to turn off at 115 volts. Now let us reduce the supply voltage and see what happens. Now the supply voltage is about 115 volts, but the SCR hasn't turned off still. This is because the anode current is not 0 and the voltage across SCR is still very small. The SCR would turn off when the anode current falls to 0 and the anode voltage equals the supply voltage. In order to monitor the anode current more precisely, we will need a milliammeter of a lesser range. So, now we are using a milliammeter of 0 to 10 milliamps range. Now let us reduce the supply voltage further and see what happens. The anode current is reducing. And now it abruptly goes to 0, implying that the SCR has turned off. Let us watch that again. I increase the voltage to turn the SCR on. Now it is on, so I reduce the anode voltage again. Now you can see that the anode current is reducing. Now it is about 2 milliamps. Now it is about 1 milliamp. And now it abruptly goes to 0, meaning that the SCR has turned off. In fact, an SCR turns off when the anode current falls below a certain value. In this case, this value is about 1 milliamp. But why does that happen? When the SCR has turned on, the depletion layer at J2 no longer exists. Therefore, device stays on even when the anode voltage is brought down to 115 volts. Only when anode current is reduced significantly, the depletion layer comes back into existence and the SCR turns off. This value of anode current is called the holding current, IH. Thus, holding current is that minimum value of anode current which must flow in order to maintain SCR in on state. Similarly, when the SCR is to turn on, a minimum number of carriers must be allowed to flow so that compensation of depletion layer at J2 may take place. Thus, a minimum value of current must be allowed to flow in order to turn the SCR on. This value of anode current is known as latching current. Latching current is that minimum value of anode current which must flow in order to turn the SCR on when VBI is applied. Generally, latching current is almost equal to holding current but slightly less than it. Both are of the order of a few milliamperes. Therefore, the VI characteristic graph so far looks like this. The SCR does not turn on until the anode voltage reaches the breakover voltage, provided at least latching current is allowed to flow. Once the SCR turns on, it does not turn off until the anode current falls below the holding current. Till now, we had kept the gate open, that is, the gate current was 0. Let us now see what happens if the gate current is not 0. Here you see that a supply has been put on the gate circuit in order to cause current to flow into the gate. In addition, we have put a microammeter over here to measure the gate current. Let us keep the gate current fixed at 50 microamperes. Let us now vary the supply voltage and see when does the SCR turn on. The SCR has turned on. Let us see at what voltage has it turned on. It has turned on at about 50 volts. The SCR had earlier turned on at 115 volts, but now with the gate current flowing, it has turned on at just 50 volts. That is, the breakover voltage has reduced. So we can say that the presence of gate current causes the breakover voltage to reduce. But why does that happen? Let us try to look at the structure to understand that. When gate is positive with respect to the cathode, holes are injected into the P2 region. These holes increase the bias on junction J3, causing electrons from N2 region to cross over to P2 region. Out of these electrons, some reach N1 region and increase the bias on J1. This starts the process of regeneration, that is, the process of positive feedback. Ultimately, this causes the SCR to turn on earlier, that is, the breakover voltage is reduced. Generally speaking, greater the value of gate current, lesser is the breakover voltage. Now at this stage, we would also like to know the effect of the gate current on the VI characteristics. These are the characteristic curves for three different values of gate current. Ig2, which is greater than Ig1, which in turn is greater than Ig0. We see that as the value of gate current is increased, the value of breakover voltage decreases. If the gate current is adequately large, then the breakover voltage is significantly small. This behavior of SCR can also be explained with the help of two-transistor analogy. The SCR can be thought of as made up of two transistors. One is NPN and the other is PNP. Thus, anode becomes the emitter of Q2 and cathode becomes the emitter of Q1, and P2 region to which the gate is connected forms the collector of Q2 and base of Q1. If gate current is injected, the base current of Q1 will increase. Increase in base current of Q1 causes increase in collector current of Q1, which is also the base current of Q2. Thus, increase in base current of Q2 leads to increase in its collector current, which causes increase in base current of Q1. Thus, a process of positive feedback is established. Ultimately, both the transistors saturate and free flow of current takes place between the anode and the cathode. In the absence of any gate current, reverse saturation current across the junction J2 begins the process of regeneration. So far, we have kept the anode positive with respect to the cathode. What would happen if the anode is made negative with respect to the cathode? We'll first make a qualitative analysis of the behavior of the SCR in the reverse bias region on the basis of the structure of the SCR. Application of reverse bias has caused the junctions J1 and J3 to be reverse biased and junction J2 to be forward biased. Therefore, depletion layers at J1 and J3 have become wider. As we go on increasing the bias, a stage comes when junctions J1 and J3 break down. At this anode voltage, reverse breakdown takes place. This value of anode voltage is called the reverse breakdown voltage. Reverse breakover voltage is the anode voltage at which reverse breakdown of SCR occurs. However, SCRs are not usually designed to operate in the reverse bias region. Therefore, we would not actually perform the experiment to verify this. Thus, the overall VI characteristics of the SCR look like this. The forward bias region can be divided into three parts. Cutoff region, where the voltage across the device is large and the current through it is very small. Negative resistance region, where the device exhibits negative incremental resistance. And saturation region, where the voltage across the device is small and the current through it is large. In the reverse bias region, reverse breakdown occurs at VBR. That completes the study of the VI characteristics of the SCR. Before we end this program, let us quickly summarize what we have learnt up till now. When anode is positive with respect to the cathode, SCR turns on with the application of breakover voltage. Once SCR turns on, it remains on until the anode current falls below the holding current. If some gate current is also flowing, then breakover voltage decreases. Greater the value of gate current, lesser is the breakover voltage. In the negative bias region, reverse breakdown occurs at reverse breakover voltage.